yesterday we did, or Friday, whatever, a lab on calorimetry.
Yeah.
Did we talk much about it at the end?
No.
Okay. Let's talk about it real fast. In that lab, we took NaOH, we dissolved it in water to produce H plus and OH minus. When we did that, the temperature went where? Up or down? It goes up, right?
Yeah.
It got warmer. Yeah, I don't know. It's an A plus. I have no idea what I just did here.
Wow.
You're all right.
You're like Andy Warhol.
I guess. So Na plus plus OH minus, it gave off heat. All right. We were able to use S equals M, sorry, Q equals S M delta T to calculate this heat, right?
Yeah.
All right. And S was 4.184. M was like 50 something, 50 point something. I don't know. How much mass did I give you?
It was like 30 something.
What?
Actually, I have no idea.
The mass of NaOH.
You
Oh,
didn't give us.
it was 4 point.
It was like
Our
3
total
point.
was 4.4.
Did you subtract?
Yeah, ours
Did you
was 4 point.
subtract out the wayboat?
Yeah, so it was like
Okay,
4.4.
4.42. So
no.
Wait,
Do
we got
4.4 minus 0.7.
Wait, no. It was 4.4 after the label, because we had something in
Okay, well, I'm just going to go with this number anyway. It'd be different for all of you.
Oh, because it's, oh yeah.
Yeah, it's the 50 grams of water
I see what you
plus the grams of your sample. I'm going to call it 54.2 because I already wrote it. Then post, what was your changing temperature?
16 degrees.
16 or 6?
16.
Okay. Hello. How are you? Good. Thank you.
Isaac.
All right. Isaac's actually been on that slip and slide before. All right. So you've actually. All right. Then you do this math. I don't know.
Approximately
3.15.
well, that's what I got with my numbers.
All right. So don't do that math. But if we just pretend and we use Caitlin's numbers, you get negative 3.15 kilojoules. Fair enough.
Yeah.
Mm-hmm.
All right. But then we wanted it per mole, correct?
Yeah.
So I have to do this number. So that's my kilojoules. I'm going to divide it by the moles. So what was the mass of your substance again, Caitlin?
Wait. 40
So 4.4 grams was the mass of her sample, and I'm going to divide that by NaOH, which is 40, correct?
Yeah. 2.11.
And you end up with what overall value? That's this part is 0.1.
Oh.
Negative 28.6 kilojoules per 1 mole. Okay, how many have a number pretty close to 30? Raise your hands. And I mean like within 4 or 5 of 30. Oh, please, everybody.
What did you get?
All right, Dave, what did you get? Okay. All right. This is pretty good. This is very consistent for the data that we get in this class. There's only one problem with this. It should be 44 kilojoules from the book. Book lies. No. Right. So we have a very short conversation with your lab partner about how all of us are off roughly the same amount, right? So.
There's.
In that short discussion, you maybe discussed the actual cup absorbs heat and loses heat. Nope, that wasn't part of your conversation. It's okay if it wasn't, but that's the real answer. We lose heat to the surroundings, which would be the water, which is what we measure, but it would also be a little bit of the cup. It would actually be the thermometer itself also. All right, the little stir, the air around it. So the heat lost would account for this difference. Are you okay with that idea?
Mm-hmm.
All right. So we would say that roughly, we don't really need to do the math, but if we took 28 and we divided by 44, all right, times 100, that would tell us the efficiency It doesn't really matter whether it's related or not. But that tells us the efficiency of our calorimeter, because I've done this for years and years and years, and we're always right about 30. So it's not something that someone suddenly did wrong. It's the efficiency of the calorimeter itself. And no one typed that in, but it's like 33, or yeah, like 53%, 58%. So, okay. Anyway, I'm moving on. You okay with that? Okay, now, no, you don't need to turn it in. Do recall, though, on your exam, because there's a calorimetry question on it. There's an A, which is where we find Q. There's a B, where we find delta H per mole. And then, do you remember what the C piece was?
Oh, yeah, you have to like
Using something grams for how much it will take to raise the temperature.
Yeah, using delta H to find grams, given delta T. What's delta T? Change in temperature. Okay, you have to apply that. All right. Today we're going to wrap everything up. So we have Hess's law and heats of formation and how they apply. All right, our objectives are here. It's the same thing today. What we're doing, what the objectives are. The reading assignment. If you have not read everything else in the chapter, please read it. And most of you have turned that in. It's awesome. All right. But we finally have the majority of students have turned in an assignment within 1 week, and it's a new day. It's so funny in my 15-year career how much my attitude has changed. But whatever. Turn in the blue sheet, whatever that was. This is just cut and paste from the page, so that's why that's good. Okay, here we go.
what is the test for this?
The test is in a couple of days. At the earliest, Wednesday. At the latest, Thursday. Okay?
So what's
There's Thursday.
Yeah, there's a buffer.
Can you just do it Thursday? Because I'm not going to be here.
No,
Okay.
that would like, never mind, I'm not going to say that to be recorded. All right. But when someone says that, you always put the teacher in a weird position because they're going to be like, oh, okay, I'll change it for Diane. And then they're like, well, he loves Diane.
Yeah.
Or we're like Isaac.
Yeah, I bet you would change it.
Yeah, you would change it for
I do
Isaac.
love Diane, but like, I don't.
Love her as much as Isaac.
Yeah.
Yeah.
Oh,
It's
really?
tough.
I
All right.
really just want to meet this idea.
All right, here you go.
Yeah.
There's none of this on the test, so I'm going to blow through this as fast as I can. Bomb calorimetry, whatever can you say it, they can be carried out in a sealed one as well to measure the heat absorbed by the water. They are much more efficient. Because the volume of the bomb calorimeter is constant, what is measured is really the change in internal energy, not the enthalpy. For most reactions, this difference is very small. That's why we don't really care about it. But just know, hey, there are two ways to do calorimetry. Okay, then this slide just needs to be deleted because it doesn't work.
Why is it metro?
Huh?
Metro.
How come you?
Yeah, that's
Oh. Ah,
goodbye. All right, Hess's law. I tried to explain this first hour as a disaster with that outline. It's just easier to show it later with a real problem. Okay, ultimately Hess's law. There's 3 laws in AP chemistry that you wonder how on earth someone got it named after them. Hess's law says the sum of all the parts is equal to the whole. You don't have to write that down. All right?
It's pretty obvious.
This is essentially what it means. Yes, we are sure. So Hess's law, if you'll just look at the screen, it says, hey, maybe you don't know the total energy required to climb these stairs. But if you know from here to there, from here to there, and here to there, if you add all 3 of them, that would be equal to all of them.
okay.
Okay?
Wow.
Ultimately thinking, don't overthink it. This is the same thing. Yes, Coley. All right, are we okay with Hess's law so far?
Yes.
Yeah.
All right. So what it's ultimately going to say is if we don't know all
the delta H for the entire process. As long as I know delta H for the parts, I will be just fine.
Well, I'll see you probably in 5 hours.
Can't wait.
Me neither.
All right, here we go. This is his actual law here. Hess's law, don't worry about that. I feel it. It states if a reaction is carried out in a series of steps, delta H for the overall reaction will be equal to the sum of the enthalpy change for the individual steps. Now, this looks scary. This looks easy. It's the same idea. Yeah. Yeah, you can look at it that same application. Okay, so all this thing is looking at the main post of oof. It's saying, hey, we may not know the whole thing, but if we know from here to here or here to here, if we add them, they're going to be equal. That's all it's saying. Okay, now, because delta H is a state function, the total enthalpy change depends only on the initial state of the reactants and the final state of the products. That slide has been repeated like 3 times. All right, so this is going to help us do what are called enthalpies of formation. An enthalpy of formation, or delta H, I did that wrong too, I'm sorry. It's delta H with a lowercase f and an uppercase little circle that we call a knot. An enthalpy of formation, or delta HF naught, is defined as the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental forms. Okay, so that's a lot of words, but what an enthalpy of formation is when we take 2 elements or more, it can be more, but we form a compound out of them, like water.
That's all?
That's it. But we do the math now. And actually, sorry, we don't do the math. These values are known. We're going to find them in tables. But just know that the technical enthalpy of a formation is the delta H for the formation. Now look at what I point here. For the formation of 1 mole of the thing we're talking about. Now, we have to be careful. Now, do not write down what I'm going to do because it's going to be wrong. If we balance this out and it was, actually it's not. Sorry, that's a different slide coming up. We balance this out. This is 2, 1, 2, correct?
Yeah.
Mm-hmm.
All right. When we do enthalpies of formation, we only would do it for 1 mole. So you need to start getting used to seeing something like this, where it's balanced with a fraction. You'll have 1, 1/2, and 1.
Because you only want for one thing.
Don't hate fractions, because we define it for 1 mole of this. Now what this means right here, it's not really that much complicated. It just means 1/2 of a mole of O2. It does not mean O. Okay? I'm not dividing the subscript in half. I just have 1/2 mole of it. Okay? We've been able to put numbers in front of them before, and it was fine. Just know that you may occasionally see a fraction now, and that fraction is so that this value is given for 1 mole of the thing you're talking about.
So does that mean I have to find 2 moles of O and then divide it by 2? Divide it in half?
Find 1 mole of O2 and divide it in half.
Okay.
Alright. This doesn't happen very often, but you'll see it. Now you'll know why sometimes there's a half in your reaction. It's to make it so that we're defining it for 1 mole of what we're talking about. Alright, now. It's not that bad. Standard enthalpies of formation. These are very simple as long as you are very attentive to detail. So, standard enthalpies of formation, or delta HF, are measured under standard conditions. Now, do you ever said the word not and put a little circle? This little this circle implies that these things are given at a standard pressure and temperature. Okay? Whenever we have a number, like 12, and there's a circle, we've been calling it like a degree. Really, it means in reference to something. This circle means in reference to being at room temperature and room pressure. Okay? So these delta H, F, naught values are found in tables. They're not things that you have to calculate, but you have to use them to find other things. So far, are we okay?
Yeah.
Now, we do need to be careful when we use these tables. You must pay attention to the state that the substance is in. Because if I'm going to use this table and it says water, you're going to look at the table and you'll see two values for water. Well, it depends on if it is liquid water or gaseous water. The problem will tell you which one of the two that it is typically. Are you okay with that? But notice, these are different values. Okay, so what does this have to do with anything so far? Well, we're going to use this table and Hess's law to do some cool math. All right? Compared to math we have been doing, this is very not that bad. So here we go. When methane, which is natural gas, combusts, it reacts with oxygen, and it produces what? You should know this like the back of your hand now.
Oh, CO2.
All right, CO2 and H2O. When this combustion happens, even though it's happening at room temperature, it gives off enough heat that typically the water is water vapor. So that's a gas. CO2 is always a gas. Like it can be other, but it's every problem you're going to use it's going to be a gas. And methane is a gas. All right. So what we're going to do, we're going to use Hess's law. We're going to say that I don't know the delta H for this combustion reaction. But I can find the delta H for this, 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 and this, and then I can add them all together. Okay? We had a slide a long time ago that said that our change in enthalpy is equal to the sum of enthalpy of my products minus the sum of enthalpy of my reactants. Does that sound familiar?
Yeah.
Good, thank you. All right, we're going to use this table and Hess's law to make all of this work. So the first thing you should do, and if you're a note taker, I would write out the steps that you should do. The first thing you should do, almost as always, is balance the reaction. Combustion reactions, if you remember, I told you that most of the time they're easier if you'll start with the 2. Right? And then balance the carbon. And then take the number with H and put it in front of water. And then do all the math to find your oxygens, and you get a 4. Now, if I were you, you're not required to reduce this problem, but you should, because you're going to do a lot of math. And if you can find ways to use 1 in your math, life's better. So this really reduces to 1, 2, 1, 2. Now, technically, we needed to reduce it anyway because I need to report this for every 1 mole. If you don't reduce it, when you do your math, you have to divide it in half, like your answer. All right, so here we go. The next thing that you should do is find the enthalpies of reaction in the table, or formation is the right word. So I'm going to come up here.
table and I'm going to find these values. So, CH4 is methane. It's barely on the screen, but it's there. So, I'm going to just write it right down here. So, negative 74.8. Yeah, you just find the value in the chart and you write it down. And then oxygen. Please pay attention to this sentence. Oxygen, which is O2, is an element. Pure elements do not have a heat of formation unless they're in what I call a word I just forgot. If they're arranged in ways that we're not, we don't typically find them, like diamond up there. Diamond is on there, even though it's carbon, it's arranged differently. What in the world is that word? An allotrope is what I'm looking for. It means it's the same, but it's a little bit different. Anyway, so oxygen is diatomic, that's how we find it in nature, so its heat of formation is zero. It's like isotope, but different. Alright, CO2 does have a value because it's not an element, right? It's negative 393.5. Water is not a pure element either, so it has a number. It has two of them. Which one do we want? Vapor. So water vapor is negative 241.8. Okay. Now we're, oh shoot, that ungroup, whatever. The next step is to apply Hess's law or enthalpy, whatever, that our delta H, delta E, that was supposed to be an H, it doesn't really matter, is equal to the sum of the products minus the sum of the reactants. So here we go. This is where you need to be very good at keeping track of everything. All right. So the products are over here, correct? All right, we have to apply the coefficients to these values. So there was one 393, right? And how many 241s? 2. So I'm going to write this out really technical. I want the sum of the products. So I'm going to take 1, and I'm going to multiply it by negative 393.5. Now, you don't have to write it out this way. I'm just doing it to be very specific. Plus, it's a sum, all right? So if it's a sum, I know I have to add first. All right, I have 2 of the negative 241.8. Are we okay with that so far? Okay, that's the sum of my products. Now I'm going to subtract the sum of my reactants. So my reactants are over here. How many of the 74.8s do I have? 1. So I have 1 times negative 74.8 plus, since it's a sum, I add first before I do the subtraction. There are 2 oxygens, and each one of them is times 0. Now, I know that I wrote a lot of things that weren't necessary to write. You know why I write them? Because I screw up a lot of stuff in life. So, I was very technical on these, so I would try to not screw up. Okay, so now, this is negative 393.5 plus this one would be
483.
Thank you. Alright, that's a negative, right? That's not right. So that's this piece minus a negative 74.8. You with me so far?
Mm-hmm.
Now look here. What does a plus minus really mean?
Minus.
You're minusing, correct? Okay, this right here. Negative 877. Point what? 1. That's this piece. And then minus minus really means what? Plus 74.8 equals 8 802.3. And what that means is kilojoules.
Okay. So these problems aren't bad as long as you're a very good accountant. You pay attention. Like if I have an accountant, is it important that he realizes or she realizes the plus or minus sign? Yeah, for sure. All right. Now, what this number technically means, we listed this for 1 mole. What that means is if I have 1 mole of CH4, which is natural gas, CH4 has a mass of 16 grams. So if I burn 16 grams of natural gas, it will give off this much heat. Right? Most of you burned way more than 16 grams to take your shower this morning so that you could have hot water. Now, does anyone at your house use propane?
My stove.
Like your barbecue, right? All right. So propane, we're going to do the same exact math, but we're going to do it with propane now. Raise your hands if that process sort of makes sense. Okay, that's good. All right. So I'm going to erase all of this because we need this table again. And you're now going to do it for propane. Right there. It's not pointing very well. It would be. This doesn't include everything. All right, it stopped at C3, but it could go on. This table could be 1,000 pages long if we wanted to. Let's assume it is also water vapor. I will help you with propane. C3H8 plus O2 goes to CO2 plus H2O. When we balance it out, I start with the 2, that makes a 6, I take the 8, now I have 12 plus 8 is 20, which I divide in half, and I get 10. Now you would not do that because you want this per 1, so it's 1, 5, 3, and 4, and then I'll pause the video and give you a few minutes to figure this out yourselves.
I'm going to go quick just for this video purpose. So we balanced it. We know we need the sum of products minus reactants. So we got to find these things up here. Propane was negative 103.85, is that right?
Yeah.
All right. Oxygen 0. Carbon dioxide is 393. What is it? Yeah.
Yeah, 393.5.
That's
Negative.
Negative. And water was vapor, so that was negative 241.8. Correct?
Correct.
All right. And then it's the sum of the products minus the sum of the reactants. So the products I have 4, well, let's go in order. I have 3, negative 393.5. Does that sound right?
Mm-hmm.
Plus, because it's a sum, 4, negative 241.8.
Mm-hmm.
All right, and I'm going to take all of that, and then I'm going to subtract. I had just 1 times negative 103.85 plus 5 times 0. Not looking good so far.
Mm-hmm.
I won't write out all these steps, but when you do them, you are really going to have a negative here, which you add, which you're really subtracting, and then you minus a negative, which means you are actually adding. And you end up with negative 2043, is that correct? Kilojoules. Okay, that's propane. So that means if you burn 1 mole of propane, you will produce negative 2043 kilojoules. You'll give off 2,043 kilojoules of heat. Are we okay with this so far? I hope so. Okay, all this is just everything we just did. Okay, just real quick, in 2 minutes or less, there are 2 sections. You should read them, but you don't need to spend a ton of time on them. Just read them. The energy of fuels and foods. Most of the fuel and the food we eat
comes from carbohydrates and fats. If you've had an anatomy or whatever class, carbohydrates are made out of pretty much C's and H's, right? What are fats made out of? C, H's, and O's. And there's O's here. So we have O's really on both sides. If you notice when we just did combustion, what were we breaking up? C's and H's, right? So most of the energy that we really get from either when we eat or when we burn fossil fuels, it's just the breaking of carbon, hydrogen, and oxygen down into forming CO2 and H2O. Inside our bodies, it's respiration, right? It's all the same idea. We get energy from breaking complex things into simple things, and that gives energy out. Fossil fuels, all right? The majority of fossil fuels that we burn in the United States, and this is an old chart, it actually is changing. The red would be a lot bigger than it used to be. But it's petroleum and natural gas and coal. Most of our energy sources are those three, which is just C's and H's again. All right, there's some oxygens involved too, but we're basically just breaking C, H, and O apart and getting the energy out of it. Are you okay with that? Okay, good. That would be the end of any new stuff, sort of. We're now going to apply Hess's law.
Dope for $3. And the
Right.
sleeves are too short, so I wear it as a 3/4 sleeve. It has some weird Chinese writing on the back. Definitely not from America.
What does it say?
It's okay.
I don't know. I don't speak Japanese.
All right, I have 6 minutes to talk about part of tomorrow. Will be dedicated just to this part of Hess's law. Another application of Hess's law is that we can use reactions. Like we can add reactions where we do know the H's to combine to make a third reaction where we do not know the enthalpy. Okay.
That makes sense, but okay.
This doesn't work. I know it won't work. I'm trying to pull that work. And it worked. Okay. That usually doesn't
Will you
work.
repeat what you just said, because that didn't make any sense?
Yeah. What we're going to do with this part of Hess's law is we're going to say that I know, like I have an overall reaction. I want to know the delta H for carbon reacting with oxygen to make carbon monoxide. Okay? Now, I could look that up in a table, but we're not, for this example, we're going to do it a different way. So I don't know this value. But these two reactions, when added together in the right way, they can tell me this overall reaction as well. So when we do these steps in Hess's law, what we do is we take the 2 or 3, it could be as many as we want, reactions, and we arrange them in a way that they produce the third reaction. So if you will look, the way you do this is you look at your overall reaction and you say, all right, in one of these two, do I have solid carbon on the left?
Mm-hmm.
Yes, I have it right here. Then, right here, on the left, I have half an O2, but I'm literally going to add these two right here. This would add to how many O2s? 1.5 or 3 halves. So something's wrong here, and we'll fix that in a second. I'm going to erase all the. No, I won't. But let's look at this piece. I have carbon monoxide in this reaction on the left side. Is carbon monoxide on the left in my overall reaction?
No.
No. So it is over here, correct?
Mm-hmm.
All right. So what I have to do to get these to add to the right reaction is I have to flip the second reaction. Meaning I need the reverse reaction. When I take a reverse reaction, according to my reading and previous notes, what happens to this sign of this value?
It switches to positive.
It switches. Now I'm going to rewrite this backwards. I'm going to say CO2 goes to CO plus 1/2 O2. And then I'm going to get rid of this, and I want you to look at something. All right? CO2 and CO2 are now on the left and the right, correct? I have 1 on both sides, so I can cancel them out. If I have the exact same of something on one side and the other, it's canceled out. All right, does solid carbon between this one and this one ever cancel out?
No.
No, so I have solid carbon. All right, and then over here I now have a half, and over here I have a whole. So now I can cancel out a half of oxygen from my whole. I'm left with 1/2 O2. Now, what am I left with on the right side?
CO.
What's that?
Carbon.
Just carbon monoxide, right? Right here.
Yeah.
All right. Does this match this?
Yeah.
Yes. And I know this takes a few times to practice. I know it's a little tricky at first,
You
but now
tried
we're ready.
The
So
last
now I
one.
just do the math. I have negative 393 plus 383, and I end up with this being around 110. Negative. So, in a nutshell, and we'll spend tomorrow on it, so don't panic, I'm going to take a series of reactions and combine them in such a way that I end up with just what I want in my final reaction. If I have to change one of the steps, I have to do the same change to this number. So like in step 2, everything was right except for it was half, so I had to double everything. To get it to work out, then I was going to multiply this by 2, and then I'm going to add. I don't know how much time we have, but here's another one. To make graphite become a diamond, we can use these 2 steps. All right? Now, all I want is graphite on the left and diamond on the right. Now here I have graphite on the right, sorry, the left, so that's good. But here I have diamond on the left, correct?
Correct.
So I just have to reverse this reaction. So what do I do to this sign? I make it positive, and then I add them and get like 1.8.
Wow.
Every other thing would have canceled